Okay, let's get right into it. We're going to break down this incredible engineering puzzle that sits right at the heart of modern fighter jets. You see, they're designed to do two things that, honestly, from a physics perspective, should be completely impossible to combine in just one aircraft.
And this, right here, is the big question. This is the central contradiction of fighter design. It's kind of like asking a world-class sprinter to also be a world-class gymnast. I mean, the physical requirements for each of those things are polar opposites, and figuring out how to overcome that is the fundamental challenge for these engineers.
So, on one hand, for a close quarters dogfight, you need this jet to be an unbelievably nimble brawler, something that can turn on a dime. But on the other hand, for a supersonic intercept mission, it has to be a streamlined bullet, just slicing through the air, super stable, with as little resistance as possible. So how in the world do they pull off both? Well, to understand how they do it, we've got to start with the basics. We have to look at how designers literally tame the air that the jet flies through, and it all begins with the shape of the aircraft itself. The wing is really the main lifting surface, so its design is an absolutely critical choice. Think about planes like the Dassault Rafale or the Sukhoi Su-57. They have those really distinctive triangle-shaped delta wings. And the reason for that shape, it provides a massive surface area, which is just fantastic for generating lift and pulling off some extreme maneuvers, especially at high angles of attack. Now, this brings us to this really fascinating concept called controlled instability. It's kind of wild. Designers actually intentionally make fighters like the F-16 aerodynamically unstable. The best way to think about it is like balancing a broom on your fingertip. It constantly wants to fall over, right? But that very instability is what allows you to make these incredibly fast little corrections. For a jet, that means lightning-quick turns. The catch? It requires seriously powerful fly-by-wire computers making thousands of adjustments every single second just to keep the jet flying straight. We can actually put a number on this. So take the Rafale. Its wing loading, which is just its total weight divided by its wing area, is 536 kilograms per square meter. Now, in simple terms, a lower number here means the wings have to support less weight for every square meter of area, and that translates directly to better, more sustained maneuverability. Now let's compare that to a classic, the F-15 Eagle. It has a slightly higher wing loading of 545 kilograms per square meter. So what does that tell us? It tells us this was a design choice that favored more stability, especially at really high supersonic speeds, over having the absolute tightest turning performance in a dogfight. So you see, there's just no single perfect wing for every situation. A wing that's designed for the ultimate agility is going to have penalties when it's going supersonic. And a wing that's designed for a high-speed dash, well, it's not going to be the champion in a low-speed dogfight. Every single design is a trade-off, and it's all tailored to what that aircraft's primary mission is supposed to be. Okay, now let's talk about the power. If the aerodynamics are a big compromise, the engine faces an even bigger problem. See, an engine that works perfectly when you're taking off from a runway is fundamentally different from one that can shove an aircraft past the speed of sound. At low speeds, you absolutely need a turbojet or a turbofan, with all those complex rotating blades to compress the air. But once you go supersonic, those same blades just get in the way. A simple ramjet, which is basically just a very carefully shaped tube, is way more efficient. And then if you want to go hypersonic, you need a scramjet, which is an even more extreme design. Each of these engines has its own ideal operating range. And this chart just illustrates it perfectly. Take a look. The vertical axis is something called specific impulse. It's just a way to measure fuel efficiency. The higher the number, the more bang you get for your buck, fuel-wise. And you can clearly see these sweet spots where each type of engine excels. A turbojet is great at low Mach numbers, but its efficiency just plummets as you go faster. And that's right where the ramjet takes over. And then, of course, the scramjet at even higher speeds. No single engine can dominate the whole speed range. It's just not possible. So if you need different engines for different speeds, how can one aircraft possibly do it all? I mean, you can't exactly pull over at 50,000 feet and swap out the engine mid-flight, right? This is the puzzle. And the solution to this puzzle is one of the most brilliant things in all of aerospace engineering. The answer isn't to have a bunch of different engines, but to have one engine that can act like different engines. They call it a combined cycle engine. This concept design gives you a great idea of how it works. At low speeds, it operates like a traditional jet engine. But as it accelerates, all these internal ducts and flaps start to move, redirecting the airflow, bypassing the main turbines, and boom. It effectively turns the engine into a ramjet and then maybe even a scramjet. It's one piece of hardware that can literally transform itself to stay in its efficiency sweet spot across the entire flight.
Okay, so let's see how this all comes together. We've seen the compromises in aerodynamics, we've seen the challenges in propulsion. Now let's look at the incredibly delicate and often conflicting balancing act that's required to create the final aircraft. This quote from our source material just captures the essence of fighter design perfectly. There is no single best answer. There's only the best set of compromises for a specific job, whether that's air superiority, ground attack, or a high-speed interception. And here are just some of those big trade-offs. That delta wing that's so good for supersonic flight, yeah, it can be a bit draggy when you're flying slow. Those sharp angular shapes you need for stealth, they aren't always the most aerodynamic. And that controlled instability we talked about, it gives you incredible agility, but it adds all the weight and complexity of a flight control system that can absolutely never, ever fail.
This balancing act exists right down to the nitty-gritty of engine selection. This table here ranks 3 different engine cycles. You can see the pure turbojet is ranked best for supersonic fuel consumption and for simplicity. But check out the mixed-flow turbofan. It's #1 for subsonic fuel economy. It all comes back to, what does the mission demand the most?
And this chart, wow, this really shows the cost of that compromise in stark terms. Flying an F-22 at a normal subsonic cruise speed burns about 4,000 liters of fuel an hour, which is a lot. But to push it into supersonic cruise, that consumption triples to 12,000 liters per hour. Almost all of that extra fuel is just being burned to overcome a massive increase in aerodynamic drag, called wave drag. Speed is incredibly expensive. So, the crucial point here is that the perfect fighter just doesn't exist. It can't. Instead, what we have are these absolutely incredible flying machines. Each one is a unique and, frankly, beautiful solution to an impossible set of questions, a true masterpiece of managed compromises. And that kind of leaves us with a final thought about what's next. The current generation balanced speed, stealth, and agility. But as the battlefield evolves with hypersonic threats and intelligent drones, what's going to be the next great compromise? What seemingly impossible physics problem are the engineers of tomorrow going to have to solve?